In this video, we're going to talk about piecewise functions. So a piecewise function is a function which is defined differently on different parts of its domain. So we've actually already seen an example of this. So recall the function, the absolute value function. So recall the function f at x equals absolute value of x. If you remember the way we wrote that or one way to write that is as two different pieces, as x if x is bigger than or equal to 0, and as negative x if x is less than 0. So we talked about this in the absolute value video. But this right here is what we would call a piecewise function, because it's defined using two different equations on different parts of its domain. Right? On one part of its domain, x bigger than or equal to 0, it's defined using the equation f at x equals x. And on this part of its domain, it's defined using the equation f at x equals minus x. So this is a piecewise function because it's defined using a different formula or using a different equation. On different parts of its domain. And in the absolute value video, we graphed this function. I'll just sort of quickly do that again, just as sort of an example of how you graph these piecewise functions. We'll do another one, a little more complicated one, after. But remember, there's two different functions going on, right? So when you graph, you're going to be graphing sort of two different equations. One of them would be f at x equals x, so you're going to graph the curve y equals x, but this only applies when x is bigger than or equal to 0. So we know that we know what that is, right? We know that's a line, y-intercept of 0, slope of 1. So that looks like this. And notice I'm only graphing when x is bigger than 0, right? X equals 0 is here, so I only graph bigger than that, so to the right of that. So this is piece 1. Piece 2 would be the curve y equals negative x, right, for the second part. F at x equals negative x, so that's the curve y equals negative x. And this only applies when x is less than 0. And again, we should know what this looks like. This is a line, negative slope, a slope of negative 1, and again a y-intercept of 0. So these two sort of pieces, these two curves, over their given domain or given portion of the domain, combine to make one function, f at x equals absolute value x. So this is what we mean by a piecewise function. So it has two different equations or two different pieces, but it's combined to make one function. So let's look at another example. So a function f is defined as, so f at x, and it's going to be a piecewise function. So when we do piecewise functions, we put this big bracket, x plus 1, and it could be anything. It could be any equation you want, like any type of function you want, you can use to make these piecewise functions. So x less than or equal to 1, and x bigger than 1. So we have a linear piece and a quadratic piece, but it could be anything. You could have a trig piece, you could have an exponential piece, any type of function you know, or even ones you don't know, but obviously we'll stick to the ones you know for now. And now we can answer some questions about this function. So let's say we wanted to evaluate at some values of x. So let's say we want to evaluate f at 0, f at 1, and f at 2. So f at 0. So in this case, x is equal to 0. Well, we have to decide which piece of the function we're going to use. So x is equal to 0 falls under this piece, right? Because if x is 0, 0 is less than or equal to 1, so we're on this sort of branch or this piece. So we're going to be using the equation x plus 1. So in this case, x is 0, so we'll say 0 plus 1 equals 1. So f at 0 is equal to 1. How about f at, what was the next one? 1. F at 1. Which piece are we going with? Well, x in this case is equal to 1. That would again fall under this piece right here. Why does it fall under this piece? Well, 1 is less than or equal to 1, so we're going to use this piece again. So we'll use the piece x plus 1, which would mean 1 plus 1 is equal to 2. So f at 1 is equal to 2. F at 2, so now x is equal to 2. Well, now we fall under this piece because 2 is obviously bigger than 1. So we're on this piece of the function. So we're using the equation x squared. So since x is 2, we will have 2 squared, which is equal to 4. So f at 2 is equal to 4. So that's how you evaluate different points at a piecewise function. You just decide on which piece you're on, which piece you need to use, which equation you need to use, and then evaluate it like you would a normal function. So we're going to graph this function. Maybe it'll help if I rewrite it. So f at x equals this was x. Nope, sorry, it was less than, I believe. Less than or equal to 1. Should be equal to, and x bigger than 1. So we're going to graph it just basically the same way we did that absolute value function. I'll draw my xy plane. Standard tilty y-axis, I don't know why. X, y. Okay, so now what we're going to have to do is graph sort of these two functions on the, or these two curves on the appropriate x values. So the first one, f at x equals x plus 1. Well, that's just the curve y equals x plus 1. But this one only applies when x is less than or equal to 1. Well, we know what that looks like. It's a linear equation. It's a line. Y-intercept of 1, slope of 1. So y-intercept of 1, slope of 1. So that's a line just going like this. One other thing you might want to put on your graph is sort of the boundary point. Sort of our function changes at x equals 1. Right? At x equals 1, it goes from this function, or this curve to this curve, or this equation to this equation. So x equals 1 is right here. So sometimes what I'll do is I'll just draw a line at x equals 1. Dotted, because it's not really part of the function, but it helps me see where I need to change. So now what I'm going to do is I'm going to graph y equals x plus 1. So y equals x plus 1. And remember, I'm doing this for the values x is less than 1. So that's right here, right? So it goes down like that, but then I have to stop when I hit this line x equals 1. I'm going to put a solid dot there, and the solid dot is because it's less than or equal to 1, so we include this point. It's sometimes useful to actually make sure that that boundary point is sort of very specific, that you're right on the point, and this point is when x is equal to 1, f at x is equal to 2. So that's the point we're at. So this was sort of piece 1. Piece 2 is going to be the curve y equals x squared, and that applies when x is bigger than 1. So we know how to graph this, grade 10. It's a parabola, vertex 0, 0, opening up. Not too hard to do. The one sort of tricky thing that sometimes throws people off is normally when you graph a parabola, you start at the vertex, which would be right here. But the problem is this point is not bigger than or equal to 1, right? X equals 0 is not bigger than or equal to 1. So you kind of have to start the parabola over here. So what you can do, and what a lot of people do, what I'll do is they'll, at the very least, either they'll sort of very lightly sketch the whole parabola, over its whole domain, or at least think about the whole parabola over the whole domain. And this parabola, I mean, I've obviously done it for values not just bigger than 1. So what I'm going to do now is I'm going to just kind of fill in the points I want, like darkly, with a, fill that in and make it more obvious. Okay, so I'm only doing x bigger than 1. This part less than 1, I don't actually want that. Now it's going to be an open hole, an open circle, because I don't include it. It's not including 1. And this point, this open hole, if x was equal to 1, this would be 1. So this point right here, the height of this open hole is 1. And now, what do you do with this part? Well, if you've done it really lately, you could probably just leave it. But if you want to get rid of it, because it's not really part of the function, just take an eraser and try not to erase everything else, but just erase the part of the graph you don't want. Okay. So this function, these two different pieces, is the function f at x that we just graphed that right there. Okay, so that's how you graph a piecewise function. Now we could talk about stuff like the continuity. Is this function continuous? And the answer to this question, well, it would be no, right? Remember, continuous meant there was no breaks or jumps. Well, this one has a break. It has a break right at x equals 1. So the answer would be no. And if you remember from the previous video where we talked about continuity, we called this a jump continuity. There is a jump discontinuity at x equals 1. So at x equals 1, you're going along nice continuous function, and then you jump down to this other piece, and then goes on continuous. But you kind of had to jump from one piece to the other. So this is an example of a jump discontinuity. And these jump discontinuities are going to come up in these piecewise functions sometimes, where it'll always come up at the boundary point where you switch from one function to the other. And it will come up when these two pieces don't meet up. Sometimes you get lucky and sort of the parabola, well, not lucky, but sometimes it happens that the parabola would meet this line, or whatever the curves are, they'll meet at the same point when you switch from one function to the other, or one equation to the other, one curve to the other. But sometimes they don't, and that's where you get a jump discontinuity.